Good evening, and thanks for joining a special T³ International Conference TI Technology webinar hosted by Texas Instruments, where tonight we'll take a look at exploring the mathematics of wheels and spirographs with TI-84 plus technology. While we're saddened at the cancellation of this year's T³ International Conference, we're really excited that we're able to bring to you some of the most amazing sessions that were scheduled for the conference this year. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm excited to be joined by our presenter tonight, Debbie Post. Debbie recently retired after teaching math in Georgia for 41 years. Although she's taught almost every math and science class offered, her favorite classes to teach were geometry and pre-calculus, and she loved coaching the math team. She was the Teacher of the Year twice, Star Teacher 7 times, and the Presidential Award winner in 2001. Debbie's been a T³ instructor since 1995 and presently resides in Marietta and serves as the Executive Director of the Georgia Council of Teachers of Mathematics. Debbie, it's great to have you with us tonight.
Thank you, Michael. It's good to be here.
Debbie, let me give you control.
Okay.
And once I do, you can share your screen.
Fantastic. Okay, I think I've got you on email instead. So let me get back to PowerPoint and start at the beginning. All right. We're going to start at the beginning here. Thank you. Tonight we're going to look at the mathematics of wheels and spirographs. And the objective of this, participants should be able to graph the unit circle parametrically, model the motion of a Ferris wheel, model the motion of a car wheel, and then create a spirograph type design. Now, disclaimer, warning, I tend to get excited and talk fast. If I happen to do that tonight, please let Michael know so he can slow me down. The mathematics of this is really too beautiful to lose. For those of you that feel very, very confident working with the TI-84, you're more than welcome to join along with me. However, if you get lost, please don't worry about that. Just relax and enjoy the video, because in the end, I've loaded up a PDF of this entire PowerPoint so that you can have it when we're through. Okay? Ready? Here goes. First of all, we're going to start with the unit circle. Now, the unit circle to me is a beautiful figure because every ordered pair on the unit circle is an ordered pair cosine sine for the angle, the standard position angle that is subtended. In other words, the x values are the cosines of the angles, and the y values are the sines of the angles. So let's start by graphing this unit circle parametrically. Now, for people who aren't familiar with parametrics, I love parametric equations because they allow us to see x and y as independent functions of a common variable. Now, in physics, the common variable, called the parameter, is usually representing time. But right now, we're going to let t represent angle measure. So the first thing I'm going to do is open up my Smart View. If you've never played with Smart View, remember that there's a free 6-month subscription for Smart View right now on education.ti.com. So you're more than welcome to play with it. I like it. In order to graph something parametrically, the first thing we need to do is change the mode. So I'm going to press the mode button, and you'll notice that one of the options besides function is parametric. So I'm going to press parametric and hit enter. If you're using an older version of the 84, it just says, I believe, para, P-A-R-A, but you get the same effect. Now that we're in parametric mode, why don't we hit y equals? And we're going to type in the ordered pair, x being cosine of t, and you'll notice I just hit that xt theta n button, and the calculator knows that I'm in parametric mode, And so I'm going to enter two equations, one for x and one for y. And it needs to put in a t instead of the usual x we get. And the y is the sine of t. Now, with a different kind of operating system, well, a different kind of function graphing, I should say, the next thing we need to look at is the window. So let's look at the window. All right, right now I've got from 0 to, I have no idea what that is. But if I go around the circle, it should be 2 pi. So I'm going to type in 2 pi. And that t-step, if I'm not badly mistaken, is pi divided by 24. You want a t-step, well, basically, let's go back to parametrics a little bit. The way the calculator graphs parametric equations is, it's going to plug in every value from 0 to 2 pi and plot those values, and because I've told it to, connect the dots, okay? You want a t-step that's small enough to be able to plot enough points so that you see your figure. If I'd left my t-step at 6, I would have gotten basically 6 points. Well, technically 7. 0, 1, 2, 3, 4, 5, and 6. And it wouldn't have probably come back to 2 pi because it wouldn't have hit it. So that's why that default is pi divided by 24. It gives you a circle, well, or at least close to a circle. Now, one more thing, and I forgot to mention it. When I was at my y equal, I was graphing in, I call it football notation. That means if I move my cursor back behind the equal sign, I can change this pressing enter to change different colors. I like blue. But more importantly, I can change the line so that it either looks like a single football that goes around, well, kind of a dotted line, but a really more of a dotted line, a regular line, a thicker line, or the one I prefer, which is a football that creates a path. And let me tell you why I do this. It slows the calculator down just a little bit, and I like seeing where the cursor is. Frankly, that's why I like using the 84, because it graphs slow enough to where you actually see the graph develop. I know that a lot of you like a graph that just suddenly appears, but to me that kind of takes all the joy out of watching the graph appear right before you, or develop before your eyes. To me, I think you get a better conceptual understanding when you watch points being plotted. And now I'm going to hit graph. Oh, well, wait a minute. Yeah, I'm going to hit graph so that you see what it looks like. All right, you see a graph there. Unfortunately, I have a format on, so I'm going to change my format. I have a background image. I was playing with this earlier. I will show you how to put that image on later. And I'm going to have a background of white. So let's do that again. Watch the graph develop. Oh, it won't develop until I hit another key again. So let's hit cosine again. Now let's watch it develop. You see, you actually see the t values go all the way around the unit circle and the order pairs being plotted. I think that graph is just beautiful. Well, enough about the unit circle. And just to remind you what I did, I changed the mode to parametrics. I typed cosine t and sine t in the y equals. I changed the window to go from 0 to 2 pi. And I let the graph, oh, I should have mentioned something about my x mins and x maxes. This is zoom decimal. I like zoom decimal because your x and y's are measured in the same size units. And that's the graph we got. Now, enough about the unit circle. What's the difference between a circle and a Ferris wheel? If we were doing this interactively, I'd ask you to give me a whole bunch of options. But since you're not, I'll go ahead and tell you what you'd probably tell me. And the first thing you'd probably say is, there's a different radius. And you're absolutely right. I'd probably ask you for your favorite radius, but since you're not here, we get to use my favorite Ferris wheel, which is the Atlanta Skyview, which has a radius of 83 feet, and it's 34 feet off the ground because there's a loading platform. That's one of the differences between the unit circle and the Ferris wheel. Another is there's a different position. Very few of us get on the Ferris wheel where the x-axis should be. Most of us load at the bottom. So we're going to start at the bottom of the wheel. Now, how do we fix that? Well, let's think about it for a second. I'm really going to let you think about it. Okay. To fix the radius, we're going to change the coefficient of the trig functions to 83. To raise the Ferris wheel so we don't go underground, we're going to add 83, which is a radius, plus 34, and that's the loading platform, to y of t. Okay? I only have to add it to the y because I'm dealing in parametrics. Now, this results in the equations x of 1t is 83 cosine t, and y sub 1t is 117 plus 83 sine t. So let's change our calculator to fix that. I'm going to insert an 83, and to insert, I just hit second, delete, in front of my cosine, and in front of the sine, which is the y value, I need to insert 117 plus the sine of plus 83, times the sine of t. Now, I'm going to have to change the window. So let's go to the window and see what it looks like. I'm still measuring angles, so I'm not going to change my t value. And we'll change the time in a minute, by the way, okay? All right, because I know I should not be measuring angles, trust me. But my x minimum is not going to allow me to see the graph unless I let the minimum be somewhere around negative 83. I'm going to say negative 5 to give myself a little bit of breathing room. Change the max to 85. And if I was counting from negative 5 to 85, I'd probably count by 20. The y's need to go from about 0 to, well, the sky view says it goes up to 200, so let's go to 200. And once again, I'll count by 20s. Now let's graph to see if we've got a decent Ferris wheel. Oh, no. I don't think the Ferris wheel looks like that. So we're going to go to the zoom and the zoom square. We're going to use option 5. This creates a square window so that the x and y axes are measured in the same size unit. Now it looks like I actually might have a Ferris wheel. However, we said there were other things wrong with it. The window needs to be fixed too, so I changed the window, and then, since it looked more like an ellipse, I pressed zoom and z square to make the Ferris wheel look more realistic, and the window automatically changed. Now, the other thing we said was wrong was that it didn't start, quote unquote, at ground level. In other words, y at 0 is 117 and not 34. Now, let's talk about how I know that. If I press trace, you'll notice the graph starts where my t value was 0. If I press my cursor to the right, the trace values increase by using increasing values of t. Now, needless to say, those weren't exactly the ones I wanted. What I'd really like is for the cursor to start here at what I call the loading platform. And then I'd like it to go over to this point. I'd like it to go to the top, continue down to here, and then come back. So let's talk about how we can fix that. We would like the y values to start low at 34 and end high at 200. And if the Ferris wheel is still moving counterclockwise, the x value should start at 0, increase to 83, then decrease to negative 83 and come back to 0. I put these values in a table so we could see them. And in my list 1, I put the points of the angle that correspond to the axes. So in other words, this is 0, this is pi over 2, this is pi, 3 pi over 2, and 2 pi. And I wanted the x's to start at 0, move to the right 83, go back to 0, move to the left negative 83, and then end up at 0. Okay, what does that look like? I graphed it, it looks like this. And that doesn't really look like a cosine graph. I could use a phase change, but because it's something I'm doing later, I'm going to really call it what it looks like. And that appears to be a sine curve. So as a result, the blue graph, the x values, appear to be a sine function. So I'm going to change the x equation to x of 1t is 83 sine t. Now, let's look at the y values. I wanted them to start low, the loading platform 34. Then I wanted to go up to the vertical translation, which was 117. Go up to the height that's the maximum, 200. Go back down to the vertical shift, and then down to the loading platform. And if I graph these as a function of list 1, that's what the graph looks like. And to me, that looks like a negative cosine function. So the red graph is going to change equations to 117 minus 83 cosine t. Now, let's change that on our equations. Michael, are there any questions about what I just did before I leave this page?
Debbie, so far I don't see any questions, but if people have them, please feel free to ask.
Yes, thank you. Okay, so I'm going to go back to the calculator. And this time I'm going to change this equation to be a sine t, and the height, the y equation, to be a negative, so I can basically subtract a cosine t. Now, when I press graph, basically I should see a different starting position. Let's see if this works. That's a decent Ferris wheel to ride, I think. I like that one. However, there are other changes too. And the next one is, oh, let me tell you what we did. Let's make sure people can catch up if they want to. We changed the equation to 83 sine t and 117 minus 83 cosine t to be able to graph a Ferris wheel that started on a loading platform and made one revolution. Okay? Now, another difference between the unit circle and a Ferris wheel is they have a different speed. Now we've really got to change the way we're looking at the t-value. So far, we've been looking at the t-value as an angle. Now we really need to think of that as being time. The Atlanta Skyview claims that it makes one revolution in 110 seconds. Another difference is, what if it goes in a different direction? Now, direction really is arbitrary. It depends on what side of the Ferris wheel you're standing on. But could we make this go clockwise instead of counterclockwise? Let's give it a shot. If the Ferris wheel makes one revolution in 110 seconds, we need our functions to find values of 2 pi when the t-value is 110. To change the speed, we can change the coefficient of t to be 2 pi divided by 110. If we want the Ferris wheel to go clockwise, we can change the x values to start in the negative direction. And that means our new equations are going to be sub 1t is negative 83 sine 2 pi divided by 110 times t, and y sub 1t is 117 minus 83 cosine of 2 pi divided by 110t. Now, I'm going to let you stare at these for a second. You could reduce that fraction if you wanted to. I have more parentheses than are needed, but when I'm starting out working with students, I don't mind if they see this so that they will remember that that's the coefficient of t and that it's needed, because when we plug in a t value of 110, we're going to find the cosine of 2 pi, and that's going to be representing one trip around the Ferris wheel. Okay, now let's go to the calculator and make these corrections. All right. Once again, I'm just going to insert a negative to let the Ferris wheel go clockwise. Oh, good question. My window is here. I'll just go ahead and show that real quickly. Someone asked about the window. We've got to change it, by the way. It's got to go now from 0 to 110. Because we need to go all 110 seconds. And if I'm going from 0 to 110, that t-step might as well be 1. We'll change it every 1 second. So that means that the calculator is going to calculate every 1 second what ordered pair would be graphed and then connect those dots. Okay. Let's go back and look at the window. Or sorry, my y equals. I've gotten the negative in, and I'm going to put my coefficient of t. So I'm going to insert 2 pi divided by 110. And I'm doing this to change the speed of the Ferris wheel. I could have done this all at once, of course, but too many changes at once confuse people, or at least they confuse my students. So you'll excuse me for doing this one later. What we've done now is the negative meant that our x values are going to start at the 0 and then go negative and then come back to the 0 and then go in the positive direction and then go down. And the y values are going to do the same thing they were doing earlier. You're right, I did type in 110. Thank you so much. Was that Karen? I appreciate that. Good deal, we'll fix that. Boy, I would have had a roller coaster instead of a Ferris wheel. Here goes. And that's how we model Ferris wheels. Are there any questions?
So Debbie, Kelly asked, what effect is caused by changing the argument to t minus some value?
Oh, if I change it to t minus some value, well, let's try it. I'll show you what happens. Oops. It's a great question. So I'm going to insert a parenthesis and then move over. And let's let it be t minus, well, let's see, we're going 110 seconds. So let's make our t minus 30. I think that'll be different enough. What do you think might happen? Be thinking about that. Now remember, I'm not changing my t values. In other words, I'm not changing my parameter values. All right, did I say 30 earlier? I think, let me make sure I said the same thing both times. Yeah, let's see what happens. Ready for the graph? Here comes the big reveal. Now, what do you think happened? If I press trace, because I want you to see the trace here, you'll notice my t-value still started at 0. But instead of figuring out the sine and cosine at 0, it figured out the sine and cosine at -30. So basically, in a way, I got a phase shift for each one of the equations, but that presented a new starting point on the Ferris wheel. That was a great question. Thank you. It did. It created a phase shift. In order to start it at the bottom, well, that's why I went ahead and let the t-value, well, that's why I changed this to a negative cosine and a negative sine. So, okay, I'm going to delete this one again. There we go. Yeah, I've got in the parentheses. Okay. The reason I changed the functions to be negative sine and cosine instead of the ordered pair cosine sine that we used on the unit circle is so that I could, instead of using a phase shift, use the different functions to model where the graph actually started. I didn't want to use a phase shift because the next thing we're going to do is look at a wheel, and I definitely don't want to have to complicate things further. Okay? But that's a great question. We could have definitely used a phase shift to accomplish the same purpose. Any other questions? You're asking good ones. I like this. Okay. In that case, this time we change the equations to -83 sine of 2 pi t over 110. And the y is 117 minus 83 cosine 2 pi t over 110. And the window was the same that we used earlier. And that was, well, you just saw the graph. Okay. What's the difference between a unit circle and a car wheel? Okay, if you think about the unit circle and a car wheel. Oh, good question. I wanted to show clockwise that would be the only difference, just changing the sign value from positive to negative, just to show you that you could do it. It also was a great introduction to this one, because if you think about a car wheel, the entire wheel changes position. And let me show you what I mean. I'm going to move this to a document camera. I've got a little toy car here with a sequin attached to one of the car wheels. Watch what happens as this car moves. Now, if you're watching this, you'll notice the Y values are still going up and down, the same way they were doing on the Ferris wheel. The Y values aren't changing a bit. But, let me go back. The X values are. Clearly, or the car wouldn't be moving. So the X values look like we're creating, well, I'll let you figure out what they're creating. How can we model this motion? Think about it for a second. All right. Now, I'll be honest with you. I gave you a lot of wait time there. In my class, I let my students roll paper plates on tables until someone finally suggested, it looks like you're just adding a linear term to the X values. And you know what? That's exactly what we're going to do. We're just going to add a linear term to the X values. Now, I could start with the circle we had earlier, but remember, it was on a loading platform. So I think I'm going to start with a unit circle. Now, remember, this unit circle was actually moving counterclockwise. Clockwise, right? Did you notice our wheels move clockwise? So that's why earlier I wanted to start with negative sine t for the x's and 1 minus cosine t for the y's to get the wheel rotating in the correct direction. Now, I added 1 to the y's because if this is really a unit circle, then I want to move it up 1 radius. Okay. In fact, I'm going to go ahead and put this much in the calculator so that we can get it set up to do the next step. I'm going to clear out the Ferris wheel. And start out with negative sine t and 1 minus cosine t. I need to change the window because we're going to go around the circle once. We're going to go from 0 to 2 pi. And we're going to use a t-step of pi divided by 24 again. I like that t-step. And I'm going to just show you what this looks like first before I actually look at my xmin and xmax. So I'm going to press zoom decimal so you can see where it is right now. See, right now all I've got is a circle with radius 1 that is rotating clockwise. Okay. But now I need to add a linear term to make it move. And I'm only going to add the linear term to the x component. That's what I love about parametrics. If you want to make it move in the x direction, you add something to the x. If you want to change the height, you add something to the y. Let's figure out how fast this needs to go. Now, this time, t is going to represent time, not angle. Since the wheel travels a distance of 2 pi, which is the circumference, in one rotation, which is 2 pi radians, or in our case, I'm going to call that 2 pi seconds, its velocity is going to be 1 unit per second. So I'm going to add 1t, okay? That's distance equals velocity 1 times t the time to the x sub t equation. So let's go back and fix this. Okay? So I'm going to go the smart view back up again. Oh, come on, please. There. Sometimes my mouse sticks. So all I'm going to do is add 1t or add t. And if I press graph, oh well, let's look at the window because I definitely need to change the window now. I would like my car wheel to start at 0 and go to 2 pi. I could leave it at 6 to be honest with you. It's close enough. But and then I need my y to go from 0 to 2. And we can hit graph. And that's really what that motion looks like, almost. And I say almost to make it look realistic. I'm going to press zoom square again so that the x and y's are measured in the same unit. And that's what the tire wheel actually did. And that's the motion. Are there any questions about that? Yeah, I think it is. The technical term is a hypocycloid. Here's the equation, negative sine t plus t. And the y is a 1 minus cosine t, and that's the figure we get. I think it is too. Now keep in mind, if I had a wheel with a different radius, I would change the coefficient of the sine and cosine. I'd also have to change the t value to represent the different speed at which it was going to be rotating. Okay. Now, what's the difference between the unit circle and other types of wheels? And I say other types of wheels because you don't always want to look at the point on the tire rim, the tire rim, the rim of the tire. Okay, you might want to look, for example, at a point on a hubcap. Or I chose this wheel because it's kind of like a train wheel in that the track of the train would be intersecting or it would be hitting this part of the train wheel, but this, which is called a flange, I think, and I'm not 100% sure on that one, kind of overlaps the train track so that basically the train doesn't fall off the tracks. And that's a good question. I'll show you what the next one does after 2 rotations. If the point's not on the rim, the rate of the wheel won't change, but the radius will. So we can just make the radius of the wheel smaller if you want to point on the hubcap, or larger if you want to model the wheel of a train. And let's see what that looks like. Now, I changed the window here to fit 2 rotations so that you can see what's happening. You'll notice this time all I did was change the radius of the point on the tire to 0.7, which didn't go all the way to the edge of the tire. It's just a point on the hubcap somewhere. And you'll notice it doesn't hit the x-axis. And hopefully you'd anticipate that. Now, this is what would happen if we actually had a point that was on a train track, because the radius is going to be actually larger than the actual wheel. So if I change that to 1.3, we get this lovely little loop. And I love that loop. That kind of leads us right into the idea of modeling a spirograph. Are there any questions so far?
So I think Richard had a question. What if we look at more than 1 rotation?
Oh, and we just did. Okay. Let me show you what happened on that one. Okay. I'm going to change the window to go from 0 to, now, keep in mind that if all I did was change my maximum X value, in fact, you need to see this. This is kind of cool. I'll change this to 4 pi so we can see 2 rotations. Okay. I'm still only going to get 1 part of the graph because I never told the calculator to change my t-step, to go farther along the t values. I'm going to have to change this also to be 4 pi to get the, I think I can do this in 1 step and zoom square at the same time. Yeah. I have to tell the calculator to change my t values to go from 0 to 4 pi seconds in this case, and then I have to let my x values go from 0 to 4 pi as well. Is that what we needed? Okay, good. Awesome. So is everybody okay, I think, with wheels? In that case, we need to look at spirographs. First of all, for people who aren't familiar with spirographs or just haven't played with them lately, here are a couple of websites or links that I'll let you watch later. I'm not going to show them now because I'm going to make my own, okay? I'm going to use this particular figure to make a spirograph, and I'll have to, once again, here's my disclaimer, this is not a real spirograph. This is a toy that I found at the Dollar Tree. I think it's been discontinued. But as soon as I draw something, you'll know why I like this little toy. Okay. I'm going to go back to the document camera. And, okay, there we go. I'm going to draw 2 spirographs using my little toy. The first one is going to go at the very, well, one of the points on the inner gears that's farthest away from the center. And I'm just going to make my little spirograph. You'll notice I have to go around here twice. And that's my little spirograph. And if I do this using an inner or one of the inner circles, once again, it's going to take 2 trips of the smaller gear inside the larger wheel, but I still get a 3-looped figure. Now, why did I get a 3-looped figure no matter where I placed my pencil? This is wait time. Okay? And by the way, here are the two designs. The reason that all of these shapes have 3 loops is because we use the same size gear. And I said we all use the same size gear. We use the same gear for both figures. Okay. If you were actually in my workshop, you would have all gotten one of these little toys to play with. Now, the outer circle has 30 teeth, and the inner wheel has 20 teeth. The least common multiple for 20 and 30 is 60. So that means the wheel had to make 3 rotations to actually complete this figure. However, the wheel only made 2 trips around the outer circle. Now, think about that. First of all, I think this is a cool application of least common multiple, that you take the least common multiple and then divide the least common multiple by the radius, or the number of teeth in the small gear to figure out how many loops you'll have in your spirograph shape. Now, it almost looks like this time we're adding a circle to a circle, but there's a little more to it than that. If you place the pencil at the center of the inner disc, all we'd be doing is drawing a circle. It's just going to go around in a circle. The radius of that circle would be the radius of the large circle minus the radius of the disc. So we just get that circle. And I'm going to call that distance 1, because if so, this point would then be traveling in a unit circle. Those ordered pairs would be cosine t, sine t. And by the way, none of these little gears were at the center. I tried. Okay. However, we always place the pencil some distance k from the center of the disc. And that's what gives us the neat design. So let's see what actually happens when we rotate the inner disc inside the outer circle. When the disc travels through an angle of t, and that's angle AOB in the figure, D, and by the way, this was D originally. See, this was D. It rotated through angle T. So now it has coordinates cosine T, sine T. The point K units away, and that's this point, it's now called E in the figure, and it rotated clockwise. Don't know if you realize that, but as this went around, K actually went backward. It rotated clockwise. And it lies on an angle of CDF. I'm right now just going to call CDF theta. Okay. Now, what that means is, if I think about this point as being G, DG is simply in this triangle. So its length is K times the cosine of theta. Now, GE is in the same triangle, and it's going to have coordinates K sine theta. So if I'm looking for the position of K, it's actually going to be the coordinates of D, cosine T, plus K cosine theta. That's going to be its X position. Its Y position is going to be the height of D, which is sine T, minus K sine theta. So our equations will be cosine T plus K cosine theta, and the Y is going to be sine T minus K sine theta. Now let's stop. Are there any questions about this?
It looks like we're still okay, Debbie.
Okay. In that case, we need to find out what theta is. Okay, so our particular toy had 30 teeth in the outer gear and 20 teeth on the disc. That meant that the ratio of the radii was 3 to 2. So remember I told you that I was going to call R minus R1, that means that the large gear is going to be 3, and the disc has radius 2. I've kind of planned that in advance. Okay. If you look at angle theta, once the disc has traveled through angle T, remember the measure of AOB is T, that means I can find the length of arc AB, because the length of an arc is simply the measure of the angle in radians times the radius. So if the radius of the large circle that it's rotating in is 3, then the length of arc AC or AB is now 3t. 3 the radius times t the angle. But since AB just meshed with AF, that means AF has the same length. So AF has length 3t also. All right, now, if this has length 3t, and I want to find out how large angle ADF is, I can take the arc length and divide it by its radius. So that's going to be 3t divided by 2. So that means arc AF has length 3t, but angle ADF is going to have measure 3t over 2. Okay. But if you look at CD and OB, they're parallel. So that means ADC is also t. Now, if ACD is t, but ACF is 3t over 2, then angle CDF, which, by the way, we called theta earlier, that angle is just t over 2. We're ready to graph it. Oh, by the way, in general, this angle is always going to be the ratio, the ratio of the large circle divided by the small circle minus 1. And if you think about this figure, you can probably see why that is true. Here goes. This is what we're going to try to type in. Cosine t plus cosine t over 2 is your x. The y is sine t minus sine t over 2. And I'm going to actually put the 1s in there so that you can see that change. So let's go back to the calculator. And our equation is going to be, let me delete these, clear these out. So this is going to be cosine t plus 1 cosine t over 2 and this has to be the sine of t. Start with the unit circle and then subtract, because it was going clockwise, the sine of t divided by 2. Something just came up there, but I didn't see it. It disappeared too quickly. Oh, oops. Oh, I'm going to hit on. By the way, I don't know if you know this, but pressing on will stop the motion of your graph. I need to change the window. It went 2 cycles around the, okay, let me back up. The disc went 2 cycles inside the large wheel. So going from 0 to 12, which is 4 pi, is about perfect. And I'm just going to press zoom. You will only have the PowerPoint. Okay. I'm going to hit zoom decimal. I'm sorry, zoom square. Zoom decimal. There. So that we get to actually see our little spirograph type creature. And there it is. Now, remember that the placement on the, well, let me finish with this one first. Okay. I took a picture of this and put it on my Smart View so that we could see how this looked. And as you can tell, it comes pretty close to matching, but not quite. To me, you'd probably have to blow my figure up by a factor of perhaps 2, and then move it over a half and down a half to fit it better, my students would not be happy with the way it looks. And so I played with it and altered the equation to match the picture. And what I had to do actually is increase the inner radius by 0.1 as well. But by playing around with the graph a little bit, we were able to get it that close. And the only way I could get it better is to take a better picture or else to rotate the figure. And that's another webinar. Are there any questions?
Debbie, Karen was asking why we weren't using 3T/2 or 3T.
Great question. Okay, let me back up, okay? Okay, we weren't using 3T/2 because this angle ADC was already T. Angle ADF was 3T/2. And if ADC was T, then our angle theta that we talked about earlier was only the, was only the CDF part, and 3T/2 minus T left us with just T/2. Did that answer your question? Oh, you're welcome.
I think it does. Yeah.
Okay. All right. If I need to go over this again, please let me know. I know the math gets deep. I admire y'all for attending the session, but I just think it's beautiful. I really do. Okay. I'm going to go on then. And we were able to get this to match. So what happens if we go back and change our value of 1 to something different? There we go. So I'm going to go back to y. And instead of leaving this as 1, suppose I insert and let this be 1.2. Oops, somebody didn't insert, did they? I hate it when I do that. Just retype. I know none of y'all ever make mistakes like that in class. I do all the time. Okay, let's see the difference. The little deltoid region in the middle looks larger. So does that mean that if I can go back and delete this and perhaps change this to about a 4 or 5, I should get a figure that's close to, that wasn't a delete, the other figure that I drew, in which the point was closer to the center of my little disc. And sure enough, that's what we get. Okay? Now, we played with that one. You were asking what would happen if we did change the coefficient of t, though. Look at what happens if we actually change this to 3 pi over, or 3 halves t. I'm going to put back my 1. And then change this coefficient to a 5. What's the graph? Do you notice how many loops there are? Do you think that has anything to do with the equation? I know. And this is really what most spirographs look like. I hate using the trademark term spirograph because all of these aren't spirograph designs. They have much larger numbers of gears and teeth, shall I put it, teeth on their gears, because they make beautiful designs. But I wanted a simple one to start with. Now, look at the equation again, and then remember how many loops it had, okay? I'm going to change it to 4 pi over 3. And let's see what happens, because I don't know. Okay, I'm going to pretend I don't know. Now, why do you think it stopped? Did you notice the denominator was 3? Well, the last time the denominator was 2, and so we had to go 2 trips around. This time, we have to change this to go 3 times around. Exactly. So let's change this to, instead of 4 pi, 6 pi, and we'll see the completed graph. And that's what it looks like. You notice anything about the sum of the numerator and the denominator and the second coefficient? Well, looks like I'm running out of time. I guess you're just going to have to figure that one out. But truth be known, the sum of the numerator and denominator will give you the number of loops. Thank you very much. Are there any other questions? I hope not.
I was going to say, Debbie, so far, nothing?
Okay, good. Well, in that case, that was it. Thank you very much. I had fun. I hope you did. Remember that the PDF of this is going to be available now. Is that right, Michael?
Yep, in just about a minute or so.
Awesome. Okay, thank you.
Thanks so much, Debbie.
Mm-hmm. Oh,
Debbie, I'm going to take control back from you if that's okay. I got it.
Uh-huh. There you go.
Thank you.
Mm-hmm.
To receive a certificate of attendance for tonight, go ahead and click the link that just appeared in the chat window. Also listed is a link for Debbie and my documents from tonight. And if you missed that for any reason, or if the links aren't working for any reason for you tonight, just hang tight, and we'll be sending you a follow-up email in a couple of days that will have links to the recording, the certificate, and the documents. And if you watch this on demand, go ahead and copy that link into your browser to receive your certificate. Once you leave the session tonight, if you have any other questions, feel free to reach out to us. Give us a call at 1-800-TI-CARES or send us an email at ti-cares@ti.com. Debbie, thanks so much for everything put together and shared with us tonight. We really appreciate it.
Thank y'all for staying with me. I appreciate that.
I agree. Thanks so much for joining us tonight, and we hope to see you back online real soon. Have a great night and stay safe.